Rectilinear motion. In the previous lecture we have understood that what is distance and displacement is, and from several examples it is understood also that the distance is a scalar quantity and the displacement is a vector quantity. Now we try to clarify and try to analyze and how it is, and you also see several examples depending on how the displacement can play a crucial role as a dynamical quantity in kinematics. Displacement is a vector quantity, and so it has the magnitude as well as direction. The directions from initial point to final point, and if I consider the direction from initial point to final point, then according to convention the direction is positive. If we consider direction from the final point to initial point, then according to convention the directions will be a negative quantity. So displacement's value, that is the magnitude of the displacement, is equal to that of the distance only when the path is straight line, the path followed by the particle or anything a straight line. If the path is a curved one, then this thing becomes less, should not be equal, this thing becomes less than that of the distance. That is, the distance is always greater than that of the displacement if the path is curved one, because the straight line shows the minimum distance between the 2 points. Just like if I say it is the initial point, it is the final point, the minimum distance between the initial point and the final point can be drawn using a straight line. But anything, any curve you can draw from here to here, any curve you can draw, this path or this path, these are basically referring the distance, but displacement always remains the same. The distance may vary, the displacement always remains the same. Distance may vary depending on the path, but displacement always remains the same. If I consider a scenario just like previous one, it is a 100-meter race, and the sports committee have decided to conduct this 200-meter race in this track. So the participants have to move in that direction and again returns back to this. So this is the path should be followed. But if I want to draw the displacement and direction, we know that the displacement is 0 here because initial point and the final point is same. But if I want to take it little bit, that is with time, then at t equal to 0 and t equal to 10 second, obviously the displacement is 100 meter. But after 10 second, 20 second, it again returns back here. When it again returns back, at that time the displacement becomes 0. It is again returns to initial position. So if I want to draw it, that is the x versus t curve, this is the time and this is the displacement versus time curve. So this is a t equal to 0 second, this is t equal to, I want to say 10 second, and somewhere I just extend it, that is t equal to 20 second. So if it represents the 100 meter, so t equal to 0, it is at initial point, the participant initial point, so 0, 0. When t equal to 10 second, then at that time it will reach the 100 meter, so it will looks like this. It will reach the 100 meter, okay. And when from 10 second to another 20 second passes, at that time it returns back to 0 again. So the displacement versus time curve shows this, that from t equal to 0, it starts from 0. At t equal to 10, the displacement becomes 100, that is reaches this point, and again when returning back, this shows the returning back, okay. So this is the displacement versus time curve. But if I want to show the distance versus time curve, then this is the time, it represents the time, and it represents the distance, the magnitude of it. Obviously it is not the magnitude of it, so you should not write down this. I just write s. It here refers the distance only. If it refers the distance here, then at t equal to 0 second, at the starting point, at t equal to 10 second, it is at the 100 meter. So at t equal to 10 second, it is at the 100 meter. So somewhere here, okay, it is at the 100 meter. Now at t equal to 10 second, 20 second, if I consider as t equal to 10 second, t equal to 20 second at that time, that is, it is equal to 200 meter. T equal to 200 meter. If I just connect these points, then it shows this. This is the displacement or distance versus time curve. So this is the difference between the two curves if it is returning back to the same path. Now let us consider a circular track. A circular track of radius capital R, say. So at first it moves from A to C, then comes to B, diametrically opposite point, then follows this path, that is the diameter from B to A. So this is the path. When I am following this A, C, B path, okay, that is from A to C, then C to B, at that time if I calculate the distance, the distance is 2 pi r. The displacement is 2r. When it is returning back from B to A, BA path, the distance is 2r. The displacement is 2r. So from it we can see the distance and the displacement in the ACB, in the curved path. The distance and the displacement are different. The distance is 2 pi r and the displacement is 2r. So displacement is less than that of the distance. Now it is the BA path. The distance and displacement is equal since it is a straight path. Now if I follow the total one A, C, B, A, from A to C, then again to B, then again returns A, at that time the distance is 2 pi r, sorry, this is pi r, not 2, this is pi r, so it is pi r plus 2r, and even it is pi r, it is also satisfied because pi is 3.14, so here also the distance is greater than that of the displacement, so it becomes pi plus 2r. So distance becomes pi plus 2r. Now displacement again returns back to the same point, so displacement is 0 here. Now if I consider that displacement is a vector quantity, it is basically tells us the change in position of the two, change in the position vectors of the two positions. Let us consider a coordinate system like this. We consider the xy coordinate system. In this xy coordinate system, this is the origin, this is the point P, a particle is the point P, and the coordinate of the point is x1 comma y1. So this is the vector of this point r1 vector. So the position vector can be written as x1 I cap plus y1 j cap. Now if the particle translates to the point Q, then the position vector of the point Q is determined by this r2 vector, and this r2 vector equal to x2 I cap plus y2 j cap. So this is the position vector of the point P, this is the position vector of the point Q. Now if I want to find out the displacement vector, that is the difference between two position vector, the final position minus that of the initial position, so r2 vector minus r1 vector, so it will be x2 I cap plus y2 j cap, this is the r2 vector, and this r1 vector is x1 I cap plus y1 j cap. So this thing can be written as x2 minus x1 I cap plus y2 minus y1 j cap. Now if I take 2 points on the coordinate system, and we have to find the displacement vector on this xy coordinate system. The coordinates are, let us say it is 3, 5, and it is somehow 8, 17. You have to find out the displacement vector, this one, that is here also displacement vector is this. Now this is the, if I want to find the coordinate of this point, if I say this is the r1 vector, so r1 vector will be 3 I cap plus 5 j cap. If I want to find the coordinate of this point, then if I define these as r2 vector, then r2 vector will be 8 I cap plus 17 j cap. Now this displacement vector, Taylor vector is equal to r2 vector minus r1 vector, that is 8 minus 3 I cap plus 17 minus 5 j cap. So it is 5 I cap plus 12 j cap. Now we know that the triangle law of vector addition. So if we connect this here, then just see, we can say according to triangle law of vector addition, r1 vector plus del r vector equal to r2 vector. r1 vector plus del r vector equal to r2 vector. So this is the triangle law of vector addition. This thing also you should notice. And if I want to find out the distance from this, then the distance is basically nothing but the magnitude of this vector, because here the particle follows this path. If the particle follows this straight path, then del r should be root over of 5 square plus 12 square unit, that is 13 unit. So let us take a problem. A particle moves from I cap plus 3j cap plus k cap to 4I cap plus 8j cap plus k cap. Then calculate the distance and the displacement of the particle. So the displacement can be easily calculated by the difference of these two, that is 4I cap plus 8j cap plus k cap minus I cap plus 3j cap plus k cap. So 4I cap minus I cap becomes 3I cap. 8j cap minus 3j cap becomes 5j cap. K cap minus k cap becomes 0. So what is the value of the displacement is this? What is the value of the distance? The magnitude of the displacement is distance. If the particle moves along the straight line, then it will be 3 square plus 5 square. It becomes 9 plus 25. So 25 plus 9 is 34 unit. So this is the displacement and this is the distance covered by the particle. Now just think, if you have a particle or a ball or something and you just throw it upwards, then if here is a boy and he just throw a ball upward and it reaches this maximum height, capital H, and again returns back and he catches it. So if this is the scenario, at that time if I want to find out the total distance covered by this ball, then it will be 2h, 1 in the time of ascent, h in the time of ascent, and number 2, that is the another h in the time of descent. And if I want to say what is the displacement, the displacement is, because initial point and the final point is same at the end of the journey, so it will be 0. But if I want to find out little bit each and every step, then if I take a t equal to 0, this particle is here, the ball is in his hand. At small t equal to capital T, it reaches here, and again when capital T equal to 2t, he again catches this ball. So if I want to draw this, then the distance, if I want to draw the distance, that is s versus t, it is not the vector quantity, so it is following the distance. So when small t equal to 0, it is in his hand, so At capital T equal to capital T, it is at a height capital H. After that, when capital T equal to 2T, at that time it will return gain to the height 2H. So if I just connect these two, this is at capital small t equal to capital T, it is at capital H. At small t equal to 2T, it is at a height 2H. So if I connect this, we get a straight line, that is the distance. Now if I want to plot the displacement versus time curve, that is S vector, the displacement, and the displacement versus time at t equal to 0, it is here. At t equal to capital T, it is at a height capital H. At t equal to 2t, it again returns to 0. So the displacement versus time curve is like this. So we can see here, it is evident from this, the displacement versus time curve also shows the deviation or the change is here. Two things are not different. Since it is moving along the same straight line and returns back, the displacement and distance is not same here. If the particle moving along the same path all the time, here the particle moving along the same path, so you have to care about the initial point and the final point also. Now if anyone is here at a height capital H, what he have done, he just fell a ball which is just comes out, and when it's striking the ground, we consider this thing is completely elastic collisions, no kind of energy is lost, and again this ball again returns to his hand. Now if I want to draw this, then obviously the distance is obviously h in the time of coming downward, again h in the time of coming upward, so the total distance is 2h. But if I want to find the displacement versus time, that is a displacement versus time, if I want to find the displacement versus time, at that time just see, in coming downward, if it is t equal to 0, it is here. If t equal to capital T, it just strikes the ground, and since the collision I have said elastic, no kind of energy is lost, so again t equal to 2t, it will be here at the same height. Okay, so when t equal to 0, then the ball is at a height capital H. Okay, when t equal to capital T, the ball will reaches the ground, that is here, and when t equal to 2t, it again goes up and reaches the same height. So at t equal to 2t, it again reaches the same point. So if I connect this somehow like this, and again it returns back to this point. So this is the thing. So the displacement curve, here the bending of the curve, basically I want to say this shows the change in the direction at that point, and completely opposite direction it shows. Thank you.